Today, we are going to start our study of electricity. Now, if you look at electricity, what is electricity? The only answer is everything is electricity. All around us, every single physical phenomena would have something to do with electricity. For example, if you talk about rain and thunderstorms and lightning, that is electricity, clearly, right? But your heart is beating, that is also electricity. Your brain, when it wants to send a signal to a muscle to fold it, when I'm trying to fold my hand, there is an electric signal that goes from my brain to this muscle, and because this muscle twitches, I'm able to fold my hand. So every single thing, when I'm standing on the ground is holding me up with what we call normal force. But what is normal force? It's an electric force. Everything around us is electricity. So when you study electricity, you're studying the whole universe. Okay? And electric forces are huge forces, particularly when you compare it with gravitational forces. If you have two objects, suppose I had a ball and I had this chalk piece, and I kept them like this, the force between the ball and the chalk piece is very small, the gravitational force. But if I looked at equivalent materials, just protons and let's say electrons here, the force will be trillions and trillions of times larger. So electric forces are huge forces. But wait a minute, if it was so huge, why don't we notice it? Because matter is neutral. What do we mean by matter is neutral? That is exactly what we are going to study in this chapter today, which is on electric charge and potential. Okay? So first let us start with the idea of matter. Matter, anything is of course matter, right? All of this is matter. All matter is made up of, what is matter made up of? Atoms. The question then is, what are atoms made up of? Atoms are made up of protons, electrons and neutrons. You know that protons are positively charged and electrons are negatively charged. An atom has a very small tiny nucleus, much smaller than this, but I have to draw something, so I have drawn it like this. And let us talk about an atom. Let us say this fellow has 4 protons. It also has a bunch of neutrons. Neutrons do not have any charge, but the protons have a positive charge. So the nucleus now has 4 protons, so 4 positive charges. But then this atom should be overall positively charged. No, because it also has electrons roaming around. Not all at that level, some may be here, some may be there, but they are all going around the nucleus. So because you have atoms going around the nucleus, from outside when you look at it, what is the net charge? 4 plus and 4 minus. It turns out that a proton has a charge of plus 1.6 into 10 to the power of minus 19 coulombs. Plus. But an electron has a charge of minus 1.6 into 10 to the power of minus 19 coulombs. Exactly equal. So how much is the total charge in the nucleus? Plus 4 times this. What is the total charge outside? Minus 4 times this. What is the overall charge? 0. So the net charge is 0. So net charge on an atom generally tends to be 0. But matter is made up of atoms. The number of protons is exactly equal to the number of electrons. So because of this, what happens is that atom is neutral and matter is made up of atoms, so matter is also neutral. Okay? But then when will we feel any kind of electrostatic force? When will we feel forces that are due to these charges? If it is perfectly neutral. What happens is if I took 2 objects like this and I brought them next to each other and then I rub them, sometimes I can transfer electrons from one object to another object. So let us say I have here a ball and I have here the chalk piece. And if I transferred electrons, let us say I transferred 6 electrons from the ball to the chalk piece. Before this, how many electrons were there? Trillions of electrons. So, okay. So for now, I will say that there were 10,000 electrons. But there must have also been 10,000 protons. Correct? So what is the total charge? This will be minus 10,000, that will be plus 10,000. So what will be the total? 0. But now what I have done is I have taken 6 electrons. Similarly, in the chalk piece before, let us say there were 4,000 electrons. And then there were 4,000 protons. Of course, it won't be 4,000. I want you to understand that it's 4,000 is just a number. Actually, you have trillion electrons. You have huge number. I'm just writing 10,000 and 4,000. But once I transfer 6 electrons, the number of protons has not changed. The number of electrons is reduced by 6. So what is going to be the total charge? Plus 6 electrons. Plus 6, right? Into, we call this E, because whether it's plus or minus, we use E to say 1.6 into 10 power minus 19. So the charge is plus 6E. Whereas here, this is total 0. And how much has come in? 6 electrons. So this total charge will now become minus 6E. Why is this minus 6? So does it mean that you only have 6 electrons here? No. You have 4,006 electrons. But you have only 4,000 protons. Whereas here you have 9,994 electrons. And you have 10,000 protons. So that means this has excess of protons. This has excess of electrons. But notice that it was not the proton that moved. What moved? Only electron moved. When you have positive charge, it is not as if protons comes in. It's usually electrons moving. Why do electrons move? Why can't protons move? Because while the charges are both equal, mass of the proton, the mass of the proton is almost 2000 times mass of the electron. This is huge. So if a proton is like this, electron is like this. This is an electron, this is a proton. Charge, same charge. This is minus 1.6 into 10 power, right, minus 19. This is plus 1.6 into 10 power minus 19. Same charge. But this mass is 2000 times that mass. So if I try to push this electron, a small force, electron will run. Whereas with the same force, the proton is going to take a lot of effort to move. So whenever you want to move, electrons are so much easier to move. Also remember, electrons are on the outer edge. So when I bring two things together and try to rub them, it is easy to move the electron. The proton is deep inside. So to pull the proton out is going to be very hard. So in general, whenever you say charge moves, what moves? Electrons move. Some rare cases you can also have ions and protons moving, but very, very rare. Almost in all cases, it is the electrons that are moving. So if somebody has positive charge, what does it mean? Oh, electrons ran away. Somebody has negative charge, what does it mean? Electrons came in. Does it mean positive charge, you have protons moving? No, it just simply means electrons ran away. Okay, so is it easy to move electrons from one atom to another? Yes, actually it's quite easy. I will show you with a simple experiment. There are some materials which like to pull electrons and some materials which like to give away electrons. The ones which are able to pull electrons will get negatively charged. So let us do a small experiment to understand this better. Now let us look at these two straws. So these straws are made up of atoms which are all neutral. Okay, and if you look at this paper is also basically neutral. Now what I'm going to do is I'm going to rub this straw and I'm going to press it really hard against the paper and I'm going to pull it. So then I'm bringing the atoms of the straw very close to the atoms of the paper. It happens that this plastic material that the straw is made up of, the atoms like to pull electrons. So they are going to take electrons from the paper onto this. So the straw is going to become what? Negatively charged, right? Because electrons land up here. But then electrons left from here, right? So that means the paper is going to become positively charged. So let us do that and see what happens. So I'm going to place these two like this and I'm going to pull them really hard. So all I'm doing is to rub the straws and now this straw is negatively charged and you can see that this fellow is running away from this other straw. Why? This is negatively charged, that is also negatively charged. You can see that. Right? Now, what will happen if I brought this? Remember that electrons came from here to there. So that means that must be positively charged. So let us try to bring this close to this fellow. Can you see that it is attracting? So let me show it that way. So I can bring it like this. Can you see that it is attracting? Why is it attracting? Because this is negatively charged and that is positively charged. So what we can see from here is two negatively charged objects repel each other and a negatively and a positively charged object attract each other. If I had two positively charged objects, they will also repel. So we say like charges repel. Positive positive repels, positive negative attracts, negative negative repels. Okay, so that is the basic idea. So it is very easy to separate charge. All you have to do is to rub it, and the moment you rub, you have something pulling in electrons and something basically giving up electrons. So if electrons move from here to there, this is negatively charged and that is positively charged. Let us quickly summarize what we have learned. If I had two minus charges, negative charges, they repel each other. If I had two positive charges, they also repel each other. So we say like charges repel. Okay, and if I had a positive and a negative charge or a negative and positive charge, they attract. We can now go ahead and ask some more questions saying, what is the size of this force? How big is this force? And so on. And if we start doing that, then we will land up with an equation for force. What is the force between charges? It turns out that we will later find this, that the force between charges looks like this. But we are not going to get into it. This is called Coulomb's law. Now Coulomb's law is a very important law. We will come back to this. But at this point, this is not what I want you to look at. We are going to look at this idea in a slightly different way, using the concept of potential and energy. Instead of starting with Coulomb's law, most books start with forces because force is a very intuitive idea. But instead of starting with forces, there is an equivalent way of starting with energy and potential, and that is what we are going to focus on. Let us now look at this straw or chalk piece or something which has a positive charge. If I kept a small positive charge here, a different positive charge, what will happen? It will run, right? It is going to move from here to there, you know that already. You saw that with the two straws, that one straw is pushing the other straw. And suppose I ask you, why? Why is it running? Usually the answer that we give is because there is a force. There is a force acting on it. The force is in that direction, so it starts running. Correct? That's one way to think about it, which is perfectly fine. This is a very intuitive idea. This is something that our brains can quickly understand. But the problem with force is a vector. When you start doing calculations with force, one force is like this, another force is like this. You have to take into account the forces have direction. So forces have direction, that means you have to add them vectorially, which makes life a little bit more harder. Calculations get a little harder. We'll of course come back to it and learn it. But there is a different way in which we can explain this. And the second way is the idea of energy. Let us think about it. Suppose I ask the question, this ball when I drop, it falls down. You know that it falls down. Why does this ball fall down? Suppose I ask why. There are two answers, two ways to answer. One is to say this ball falls down because there is a gravitational force. Correct? So there is a gravitational force, earth is pulling it down, so it falls. So that is one answer, which is the force answer. But there is a very good equivalent answer. It is the same answer, but in a slightly different way, which is to say, there the ball has a higher potential energy, and here the ball has a lower potential energy. This height is lower potential energy, the ball comes down. Water, why does water go down? We say water likes to go down to the lowest level. What are we saying? Water likes to lose its potential energy. Objects like to reduce their potential energy. When we are talking about atoms, remember that when in chemistry or in physics you would have learned that electrons like to jump to the lowest energy level. Balls like to come to the lowest energy state. We like to spend money, which means we are losing money, right? But it's more fun. So same way, everything likes to lose energy. That's a very, very important principle. This has more energy. This has less energy. So I can say, instead of using force, I can say because it has less potential energy. All objects like to reduce their potential energy. This statement and this statement are equivalent. You cannot ask, hey, that is better than this or this is better than that. Both are the same. Except that is something our brains will immediately get. When you say force, you know, you get an idea because we have a feeling for force. But energy is an abstract idea, but the advantage is energy is a number. You can add two numbers. 3 units of energy, 4 units of energy, you add 7 units of energy. 3 units of force, 4 units of force is not equal to 7 units of force. You know that, right? So it's a force is a vector. This is a vector and therefore harder. This is a scalar quantity, so calculations are easier. Okay, but because force is intuitive, most people start to understand this by looking at force. But we are not going to do that. We are going to focus on energy. So I am going to say this object had more potential energy. Wait. Potential energy? That is gravitational potential energy. This is electric potential energy. So I will call that GP. Usually just call it P. But potential energy means gravitational potential energy. Whereas here what is it? Electrostatic or electric potential energy. So I will call it EP. But I'll just call it EP right now. So this has more potential energy. This has less potential energy. So this charge is moving from more potential energy to less potential energy. Is that surprising? No, all objects go from high potential energy to low potential energy. So today we are going to focus on the concept of potential energy and energy, not so much the concept of force. Later we will come back and understand force also because both are important, but energy is an easier thing to do, so therefore we will find that when we do calculations, we will use energy a lot more. Let us think about it. It is the same charge, no? So let us say that this was a charge of 2 coulombs. It is the same Q here. When the charge goes from here to there, has the charge changed? No, it is still 2 coulombs, still Q. Charge does not suddenly vanish. Then why does it have more potential energy here and less potential energy there? Because potential energy depends on position. So first very important point, electric potential energy depends on one, position, location of where the charge is. Here it has more, there it has less. Are you surprised? No, if you think about it, even with gravitational potential energy, this potential energy is the same mass, right? Mass did not change, but that potential energy is more, this potential energy is less. Why is that more? Oh, because height is more. So it depends on the location, height. The more the height, more the gravitational potential, right? Potential energy. The same way here also, basically different points will have different potential energy. Okay? How exactly it will depend on position, we will see, we'll study that. But right now, I want you to understand that it depends on position. But does this also depend on mass? Yes. So at this height, this ball and this chalk piece, do you think they both have the same potential energy? No. Which has more? The ball is going to have more. Why? Because the ball has more mass. So at this location, it also depends on mass, it also depends on position. Correct? So the same way, electric potential energy depends on position and also depends on charge. Exactly how it depends on position and charge is something that we are now going to look at next. Let us now look at some distribution of charges, some plus, minus, etc. from here. Now this fellow produces at various points, it produces a special kind of number, one number. At every place, one unique number. That number is called the potential, electric potential at that place. So let us say that this point is A. Let us say that point is B, C, D, E, F, etc. At each place there is a number. That number at A is called the electric potential at A. The symbol we use is VA. So we will say VA is something, some number. Let me just say that this number is 15 volts. The unit for this is volts. At B, you may have some other number. So let us say at B, I have a potential VB, which is equal to, let us say, 5 volts. Okay. At C, I have a potential VC equal to minus 2 volts. It can be negative. Now every time writing volts is a bit of a pain, so we start using the symbol V. So at D, you may have a potential VD, which is 40 volts. Notice that this is also V, that is also V. Don't get confused. That is a symbol for volts, whereas this is saying potential at D. So what is VA, VB, VC, VD? And similarly, you will have at E. For example, you may have minus 2.5 volts. There you may have 7.6 volts. At each point in space, including here. I am standing here, right next to me, there will be a point here and there is a potential there. If I bring some more charges, I change this charge, I take away some charge, bring something else, what will happen is all these numbers will change. You will get new numbers. But after that, again you will have a new number. So instead of 15, you may end up with 25. Instead of 5, you may end up with 40. Okay, but this number, that number will be one number for one configuration. So one distribution will end up with one set of numbers. Notice this number is at A. This number doesn't move to any other place. This chalk piece, if you think of it as a charge, can go from A to B, but the number at A will remain at A. What moves from A to B? Chalk piece or charge. Like if this was charge, the charge can go from here to there to there. But when it comes back here, what will be VA? 15 volts. I hope the idea is clear. At one location, you have one number. These numbers are called electric potential, not energy, potential at A, B, C, etc. They are called VA, VB, VC, right? Bunch of numbers. They are all just scalar quantities, just numbers. What use is this number? We were talking about energy, suddenly we are talking about potential. Because if I brought a charge there, potential energy of the charge when you keep it at A is equal to the value of the charge into the potential at A. Remember, we discussed that potential energy depends on two things. It depends on location and it depends on charge. It's actually a product. It depends on the charge and it depends on the value at that location. Does VA depend on where is A? Yes, of course. Because at a different place you have a different number. Different place you have a different number. So if the charge was kept here, if this was Q, let us say Q was plus 2 coulombs. Okay? This is plus 2 coulombs. Then how much is the potential energy of this charge at A? 2 into 15. 2 into 15 because it is charge into potential. Charge into potential is 2 into 15. How much is that? 30. Coulomb into volts happens to be joules. So this is 30 joules. But if the same charge Q ran off to this place, when it comes here, let us say this was Q now, how much will be the potential energy at E? What will be the potential energy at E? Well, it is 2 coulombs into minus 2.5. So 2 into minus 2.5 is how much? Minus 5 joules. Is it okay to be negative? Energy can be negative? Absolutely, no problem. So it can be negative. Okay, so is that clear? Now if it was here, the same 2 coulombs, it will be how much energy? 2 into 40, 80 joules. If it was there, it will be 2 into minus 2. How much will that be? Minus 4 joules. Let us say that the charge moves from A to B. So now the same charge has landed up at B. How much energy is it going to have when it is at B? It is going to have 2 coulombs into 5. 2 into 5, 10. So it has 10 joules. Notice something. This is 30 joules, that is 10 joules. So the energy of this, the potential energy of this has decreased. Why did the potential energy of this charge decrease? Because the potential was high here and the potential was low there. 15, 5. 5 is lower than 15. The charge wants to lose energy. So if it went from here to there, it loses energy. Hey, why can't it do this? It can do this also. I have to allow it to move. If I allow it to move like this, it will move from here to there. If I allow it to move like this, it will move from here to there. So it is trying to move to a lower potential energy. Is the idea clear? For a positive charge, lower potential energy means lower potential. Think about that. Isn't it always the case? No. This is only true for positive charge. Because it's positive, 2 into 15. 2 into 15 is bigger than 2 into, this was 2, right? 2 into 5. Because it is positive charge. But suppose instead of plus 2 coulombs, suppose it was minus 3 coulombs. And if minus 3 was here, how much potential energy will it have? Minus 3 into 15. See, VA does not change. VA is always 15. The point is, what about the product? The potential energy, now, how much is it? Minus 45 joules. And when this minus 3 comes here, how much potential energy will it have? Minus 15 joules. Which is bigger? Minus 45, minus 15. Think about the number line. Minus 45 is that side. Minus 15. 0 is here, but minus 15 is here, minus 45 is there. So minus 45 is even lesser than minus 15. So will the minus charge go this way or will it go this way? Which is lower? Remember, everybody wants to lose energy. So which is lower? This is lower. So this charge, negative charge, will move in this direction. Understood? So for a negative charge, lower potential means higher energy. So positive charge, lower potential energy means lower potential. No confusion at all. For a negative charge, lower potential energy means higher potential. Because you are multiplying by a negative number. Right? Because this is a negative charge. So if you think about it, if you take this fellow and put it here, minus 3 into minus 2.5 will become plus. It will actually get a positive energy. Positive charge will get negative energy, negative charge will get a positive energy there, right? So anyway, what we have to keep in mind is positive charges are moving in the direction of lower potential. Everybody is moving in the direction of lower potential energy. But positive charges is lower potential. Negative charges move in the opposite direction. From higher, they are moving from lower potential to higher potential because they get higher energy here and lower energy there. This is higher energy, this is lower energy. They are also moving to lower energy, but they are moving to higher potential. So I hope the idea is clear. So first, most important point, I want you to keep in mind that potential energy of a charge, you can think of as the charge into the potential at that location. Who produces the potential? Somebody else. So this charge configuration produces this potential. It is not produced by this charge. It is produced by these charges. This charge will produce potential somewhere else. Okay, but this fellow produces the potential here. That potential into the charge is the potential energy of the charge. So I hope that is clear. There are two important energy principles. The first one, we have been using that objects want to reduce their potential energy. Right? We saw that. So this ball likes to lose its potential energy. That's what it wants to do. So the question then is, why can't just objects simply lose it? Because there is a much more larger overarching principle, okay, which is something that we have to remember across. Energy can neither be created nor destroyed. Energy cannot be destroyed. So this guy cannot just give it off and then lose it. It has to give it off to somebody else who must be willing to accept it. So total energy is constant, conserved. Remember, if it loses its potential energy, it reduces its potential energy, unfortunately that potential energy has to become something else. It becomes kinetic energy. And then because it has a kinetic energy, it's moving. It will go and hit something and then it will bounce back. Unless somebody else is willing to take away the energy, you have to keep your total energy. The total energy cannot be lost. It can only be given to somebody else. But objects want to reduce their potential energy, so somebody else has to accept the potential energy, right? But that means their energy is increasing. So both of these have to be satisfied, and these are two very important principles. In any situation, object wants to move in such a way that its potential energy decreases, but also in such a way that the total energy is constant. So I hope the idea is clear. It is not just one principle, it is both principles together. So whenever we talk of energy, energy conservation is a very, very important principle. Then in addition, we also say, what will the object want to do? It wants to reduce its potential energy. Now let us look at this question. Okay, there are 2 points A and B. For some reason, maybe because there are some charges here, there, I don't know what, but for some reason at A, the potential, electric potential is 16 volts. At B, the potential is 4 volts. If I took a charge, a particle which has a charge of 2 coulombs and mass of 3 kg, and I keep that charge here and I leave it from rest, and let us say that I allow it to move from A to B. So that means it's going to move from A to B. When it reaches B, it is going to have a velocity. I want to know what is the speed that it has at this point. I want to find what the speed is. How will we find it? What is the potential energy at A? Well, it is V at A into Q. So how much is that? 32 joules, right? 2 times, because this is 2 coulombs, right? So 2 into 16 is 32 joules. When the same charge comes here, that is still 2 coulombs, what is the potential energy at B? 2 times 4, because this is now 2 coulombs into 4, 8 joules. They are not equal. But what is the second statement? Total energy must be conserved. So, but this is not conserved. Potential energy has decreased, but the total energy is not conserved. How will it be conserved? Because it has kinetic energy. So what is the kinetic energy at A? Half m into v square. M is 3, but v is 0. So this is 0. What is the kinetic energy at B? I don't know, but it is half into mass 3 kg into the speed square, so v square. Remember, potential energy is not conserved. Total energy is conserved. So let us try to find the total energy. What is the total energy at A? 32 joules. What is the total energy at B? 8 plus 3v square by 2. Total energy must be the same. There is no loss of energy anywhere. So if these two are equal, 32 joules must be equal to 8 plus 3v square by 2 joules. Right? So what is 32 minus 8? 24 must be 3 by 2v square. So this is 8 into 2, 16. So that means v is root of 16 or 4 meters per second. So from this, what did we calculate? We found the speed of this particle is 4 meters per second. So this particle, when you leave it here, when it reaches this point, it reaches with a speed of 4 meters per second. So can you see how easy it is? Once you know potential, you know potential energy. Once you know potential energy and the potential energy there, total energy here must be equal to total energy there. That allows you to calculate what the speed of the object should be. So calculations and questions become extremely easy if you use the concept of potential and potential energy. We will later use this to also talk about forces, but compared to forces, potential and potential energy is very easy because it's a scalar quantity. I hope the basic idea is clear. Let us now look at a very nice and simple experiment which tells us how charged particles move when the potential changes. For this experiment, I need this thing called the Van de Graaff generator. So what is the Van de Graaff generator? It produces charges. How can it produce charge? Nobody can produce charge. So what it does is it takes negative charges. There is a small rolling frame here which actually pulls negative charges, electrons, down, and so that means this part will become positively charged. So it keeps rolling and it keeps pulling negative charges. So this basically gets positively charged. I am a conductor and I am connected to the ground, and the ground can supply me as much negative charge as possible as I want. Okay, and also I am generally considered at zero potential. Ground is at zero potential, I am also at zero potential. Now this fellow, because it's positively charged, the potential here is going to be very high, and the potential as you go further out will become smaller and smaller, as we will see. Now this metal piece, this is basically an aluminum foil, it's a metal piece. Now if I have some charges, negative charges on me, it will come on to this one. So notice something interesting. If I'm going to get this started, this metal piece wants to reach this object. Let us see that. Can you see that? And if I let it go, something interesting happens. It is going there, touching it and coming back to me. Why does it do this? Let us try to understand what we just saw. So here I have this Van de Graaff generator, right? So this is the motor that is running it, but think of it as positive charges on this Van de Graaff generator. Okay, so that stick, so this stick here has positive charges. And then this is my hand. Okay, I'm going to draw a very bad hand. Okay, so this is my hand. But my hand is connected to the earth because it's connected to me. I'm standing on the earth, so this is the earth. And the earth can supply as much negative charge as I want. So when I keep this metal foil, what is going to happen when it's touching my hand, because this has positive charges, it is pulling electrons. So this basically gets negatively charged because I'm close to a positive charge. What does positive charge do? It pulls negative charges, right? It's attracting. But of course the electrons can't come that way, so the electrons are here. But because it's pulling, this gets negatively charged. And then when I release it, because this is also negative and this is also negative, this fellow starts to move. And this moves here. This is at a high potential. So this is, let us say, 100 volts. Let us say that this was minus 2 coulombs. It is not that much. I'm just using minus 2 coulombs. Okay, but basically it is some negative charge. So at this point, the potential is 0 volts because I'm touching the earth. Okay, the earth is considered to be 0 volts, and therefore this is also 0 volts. So how much is the energy this fellow has here? 0. So the potential energy is 0. But now I have minus 2, my total potential energy here is 0. But if I came here, how much will be my potential energy? Minus 2 into 100. So my potential energy here will be minus 200 joules, which is lower. This is lower. So I start coming here. Then I come and I touch. The moment I touch, this is negative charge, and the negative charge comes onto this. But then this motor is still running. So this negative charge comes down and this still is positive. And then some of this positive charge starts coming here. Now positive and positive repel. You can think of it in forces, but you can also think of it as energy. Because once you have positive charge, let us say it becomes plus 2 coulombs. Not because positive charges move. You know that actually more negative charges will move. So more negative charges move this way, this will become positive. But once it becomes positive, how much is the energy? Not minus 200. What is the energy? It is going to become plus 2 into 100, so it becomes plus 200 joules. But if it goes there, its energy will be 0 because its potential is 0. So now it wants to go from high potential to low potential. Remember, positive charges want to go from high potential to low potential because that is when their potential energy decreases. Negative charges go from high energy to low energy, but high energy means low potential to high potential. Okay, so when it was a negative charge, it went from 0 to 100, but when it's positive charge, it wants to go from 100 to 0, because here the energy is 200. When it reaches there, potential energy is 0. So this guy now comes back. Once it comes there, what happens? This is plus charge, it's touching my hand. So now a lot of this plus charge is touching my hand. So when it touches my hand, what is going to happen? Electrons will jump and neutralize all the plus charges, but they won't stop. They will continue to add some more electrons, because this is a lot of full of electrons. So then this becomes negatively charged. So potential energy is still 0, because this potential is 0. But this is minus 2 coulombs now. If it comes back here, it will become minus 200 joules. So then what will happen? It will come here. And then it will go there. And it will come back. And it will go. And it will come. You can explain this in terms of energy. You can also explain this in terms of force. Because you can say negative and negative push each other. So this guy starts to move back, move out. And when it comes here, plus is pulling it, so therefore it gets stuck. And then once it becomes plus and plus, this will start to push. So this guy will go back, and then it will come back, and it will go back. But you can also understand this in terms of energy, right? So let us look at this again. So here I have this positively charged object, and I am going to be full of negative charges. So think of me as full of negative charges. Because of this positive charge, it is pulling a lot of negative charges, so I am full of negative charges. And if I leave this, you can see that this conducting foil, aluminum foil, is bouncing between me and the Van de Graaff generator. So as soon as it touches, it becomes positive, it jumps. Okay, because now this potential energy is very high. Because it's now positive charge, it's not negative charge. And then it starts to run to lower potential energy. Now this is low potential energy because it is 0. But once it touches my hand, it becomes negatively charged. So this is 0, this is minus 200. So this is low. So again it comes back. But once it comes here and its charge changes from minus to plus, its potential energy becomes plus 200. That is low. So it goes back. So it's not able to make up its mind. It's going back and forth like this. Nice experiment, right? The single most important point I want you to remember, so I will write it down. The most important idea is, if you had a charged object, then it produces at every location a potential. V1 here, V2 there, V3 there, V4 there. If you place a charged particle Q, its energy here is going to be, potential energy is going to be Q times V1. If you place it here, its potential energy is going to be Q times V3. Right? The potential energy at every place is determined by two numbers, the charge and the potential. Two numbers, not one. If the charge was positive, it will have the same sign as the potential. If the charge was negative, then it will get to the opposite sign. Okay? So Q times V1. V1 is decided by this guy. This object will decide V1, V2, V3. But the energy is decided by Q times V1. So I hope the idea is clear. And also remember, objects like to go from higher potential energy to lower potential energy. This means positive charges go from high potential to low. Both of them go from high potential energy to low potential energy. But because you are doing Q times V, it means if it is positive, it also means high V to low V. Whereas for negative, it means low V to high V. So this and this statement together basically is going to determine a lot of stuff that we are going to study. So I want you to really understand this well. The best way to do this is to apply it to a whole bunch of questions.